More than 80% of the universe's matter remains undetectable by telescopes and traditional observation. Despite being invisible, this elusive substance known as dark matter, which influences the formation of galaxies, the bending of light, and the structure of the cosmos. Scientists are now pushing the limits of experimental physics to determine exactly what this hidden matter is and why it's so difficult to detect. Let's rewind to where the mystery truly began. The first real evidence for dark matter came in 1933, when Caltech's Fritz Zwicky used the Mount Wilson Observatory to measure the visible mass of a cluster of galaxies and found that it was much too small to prevent the galaxies from escaping the gravitational pull of the cluster. Something else, concluded Zwicky, was acting like glue to hold clusters of galaxies together. He named the substance Dunkel Materie, or dark matter in German. In the 1970s, Vera Rubin and Kent Ford, while based at the Carnegie Institution for Science, measured the rotation speeds of individual galaxies and found evidence that, like Zwicky's galaxy cluster, dark matter was keeping the galaxies from flying apart. This didn't fit the textbook expectations. If the visible matter were all that existed, galaxies would simply tear apart due to insufficient gravitational binding. This discrepancy hinted at the existence of some unseen mass contributing to the gravitational field, and that became our earliest indirect sign of dark matter. But the evidence kept piling up. Gravitational lensing, another critical phenomenon, further strengthens the case. Gravitational lens, matter that through the bending of space in its gravitational field alters the direction of light passing nearby. The effect is analogous to that produced by a lens. One of the most remarkable predictions of Einstein's theory of general relativity is that gravity bends light. That effect was first demonstrated during a total solar eclipse in 1919, when the positions of stars near the sun were observed to be slightly shifted from their usual positions, an effect due to the pull of the sun's gravity as the star's light passed close to the sun. In the 1930s, Einstein predicted that a mass distribution, such as a galaxy, could act as a gravitational lens, not only bending light but also distorting images of objects lying beyond the gravitating mass. If some object is behind a massive galaxy, as seen from Earth, deflected light may reach Earth by more than one path. Operating like a lens that focuses light along different paths, the gravity of the galaxy may make the object appear stretched or as though the light is coming from multiple objects, rather than a single object. Clearly, something massive is there. But where is it? The term dark matter was coined to refer to this unseen mass. In astronomy, dark matter is an invisible and hypothetical form of matter that does not interact with light or other electromagnetic radiation. Dark matter is implied by gravitational effects that cannot be explained by general relativity unless more matter is present than can be observed. Such effects occur in the context of formation and evolution of galaxies, gravitational lensing, the observable universe's current structure, mass position in galactic collisions, the motion of galaxies within galaxy clusters, and cosmic microwave background anisotropies. Dark matter is thought to serve as gravitational scaffolding for cosmic structures. After the Big Bang, dark matter clumped into blobs along narrow filaments with superclusters of galaxies, forming a cosmic web at scales on which entire galaxies appear like tiny particles. So, what's stopping us from finding it? Because dark matter doesn't interact with light or regular matter in measurable ways, it passes through us, the Earth, and even detectors without a trace, or so we thought. That's where modern experiments come in, and they are becoming more precise by the year. Enter the ultra-sensitive detectors buried deep underground. Two of the leading detectors are XENONNT, located deep under Italy's Apennine Mountains, and LUX Zeppelin, housed in an old gold mine in South Dakota, USA. Both of these experiments use enormous volumes of liquid xenon, chosen for its exceptional purity and response to tiny interactions. Here's where things get exciting. The theory is that a dark matter particle, if it's a WIMP, weakly interacting massive particle, could occasionally collide with a xenon nucleus. This would produce an incredibly small flash of light and knock electrons loose. The sensors surrounding the tank are designed to catch even this minuscule activity. But it's not easy. These events are astonishingly rare. Sometimes, only one potential signal is observed in years of data. That's why the detectors are isolated so far underground, to block out cosmic rays, radioactive decay, and even minute natural background noise. Still, researchers remain determined and hopeful. The WIMP model remains popular because it fits within supersymmetric extensions of the standard model of particle physics. If WIMPs exist, they would have been produced shortly after the Big Bang and still exist today, moving slowly through space, cold, massive, and numerous. But the scientific community is no longer putting all its bets on WIMPs. Recent interest has shifted toward other hypothetical particles like axions and dark photons. Axions are extremely light, neutral particles proposed to solve a separate problem in quantum chromodynamics, but they might also be dark matter. Their defining feature is their potential to convert into photons under strong magnetic fields. And that could be the key to finally seeing them. The dark photon, on the other hand, is a fascinating hypothetical particle from the hidden sector imagined as a force carrier much like the photon in our electromagnetic world. But unlike ordinary photons, dark photons could interact with particles we've never seen, potentially acting as a bridge to the mysterious realm of dark matter. If proven real, they might unlock an entirely new force that operates beyond the standard model, offering a glimpse into a parallel framework of physics that has remained invisible until now. Now, things start to sound like science fiction, but this is a real theory. The dark sector hypothesis suggests that there could be entire families of particles, forces, or even dark atoms and dark galaxies. They wouldn't interact with regular matter except through gravity. That means our universe could be shadowed by another completely invisible and completely real. And this idea isn't just a wild guess. It's grounded in physics. These theories emerge from real calculations and extensions to the standard model. Some string theory models and hidden symmetry proposals support the possibility of mirror particles or dark forces. They also help explain why dark matter has been so elusive. Perhaps we're simply not looking in the right way. That's why the next generation tools are so crucial. The Darwin Project aims at the realization of a future astroparticle observatory in Europe as identified in the APEC roadmap. The goal is to design and construct the ultimate dark matter detector, using a multi-ton target of liquid xenon for the direct detection of particle dark matter in a sensitive time projection chamber. Meanwhile, the ARGO detector in the US will offer better background discrimination and more robust event verification. But it's not just happening underground. Space is joining the hunt too. The James Webb Space Telescope, JWST, is a space telescope designed to conduct infrared astronomy. As the largest telescope in space, it is equipped with high-resolution and high-sensitivity instruments, allowing it to view objects too old, distant, or faint for the Hubble Space Telescope. This enables investigations across many fields of astronomy and cosmology, such as observation of the first stars and the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. The earlier we look, the more we understand. The cosmic microwave background, CMB, is leftover radiation from the Big Bang or the time when the universe began. As the theory goes, when the universe was born, it underwent rapid inflation, expansion, and cooling. The universe is still expanding today, and the expansion rate appears different depending on where you look. The CMB represents the heat leftover from the Big Bang. You can't see the CMB with your naked eye, but it is everywhere in the universe. It is invisible to humans because it is so cold, just 2.725 degrees above absolute zero, minus 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius. This means its radiation is most visible in the microwave part of the electromagnetic spectrum. According to NASA, CMB fills the universe, and in the days before cable TV, every household with television could see the afterglow of the Big Bang. By turning the television to an in-between channel, you could see the CMB as a static signal on the screen. Small temperature fluctuations in the CMB, captured by satellites like Planck and soon by CMB S4, reveal how matter was distributed across space 13.8 billion years ago, and dark matter left its fingerprints in those ancient patterns. By decoding those patterns, physicists can map the density and behavior of dark matter in the early universe. This method provides one of the most precise tools for understanding dark matter's influence on cosmic history. Now let's head to Geneva, where particles collide at unimaginable speeds. At CERN's Large Hadron Collider, LHC, protons are smashed together at near-light speed, recreating high-energy conditions just after the Big Bang. These collisions produce showers of particles. If dark matter is created in the debris, it won't be seen directly, but scientists will detect missing energy, a signature of invisible particles escaping the detectors. Still, dark matter continues to evade a direct hit. So far, no conclusive evidence has appeared. But that's not failure. That's progress. Every null result eliminates incorrect paths and sharpens our models. It's like sculpting, chipping away at the stone to reveal what lies underneath. But here's the twist. What if dark matter isn't what we think it is? Some scientists believe dark matter may not be a single type of particle, but rather a range of unknown entities or even something entirely different. Could it be an emergent phenomenon arising from spacetime? Or a subtle quantum property we haven't grasped yet? And what if we've been wrong all along? A growing number of physicists explore modified gravity theories like MOND, modified Newtonian dynamics, and TeVis, tensor vector scalar gravity, which tweak the rules of gravity rather than inventing invisible mass. Though controversial, these ideas force science to re-examine its core assumptions. No matter which path is right, the implications are enormous. If dark matter is confirmed through particle detection, it would transform the Standard Model and open up new fields of physics. It might even unify cosmology with quantum mechanics. Just as electromagnetism led to the information age, understanding dark matter could revolutionize technology. Yes, it's that serious. Think about how technologies like GPS, medical imaging, and the internet were born from abstract physics. If we can grasp and perhaps harness dark matter, we could unlock innovations in computing, propulsion, or energy systems that we can't yet imagine. But beyond science and tech, there's something deeper. Dark matter challenges how we define reality. It's a reminder that our sensory world is only a small fraction of the true cosmos. We're surrounded by something vast and invisible, a silent presence shaping the galaxies themselves. That's humbling and profoundly inspiring. It challenges science to think beyond the obvious, to question the familiar, explore what lies beneath the surface, and even re-examine the equations we once believed were absolute. In the face of the unknown, it urges us not to settle for what we can see, but to keep pushing the boundaries of understanding, no matter how uncertain the path ahead may seem. So, where do we go from here? The coming years hold promise. More powerful detectors are being activated. The JWST will keep scanning the early universe. The LHC will run new experiments. And above all, scientists will keep chasing the faintest traces of an invisible world. We're closer than ever to unlocking the unknown. And yet, the possibility remains that the truth might be something no one has predicted. That's what makes the hunt for dark matter one of the most thrilling quests in modern science. Because in the end, the universe isn't just vast, it's full of secrets. Dark matter isn't just a puzzle, it's a doorway to deeper understanding. And we've only just begun to uncover them. If this topic intrigued you, share it with others, follow for more, and stay connected as we continue exploring the unseen forces that govern everything around us. There's more to discover, and this is just the beginning. Thanks for watching. See you in the next video.